Thanks very much. So my talk has 3 parts. In the first part, I'm going to discuss key-type exchange in these honeycomb iridates. Then I will focus on 2 new materials which show evidence for quantum spin liquid behavior at low temperatures. One is a new compound which has a iridium in a 4.5 plus valence state, and the other one is a rare earth-based and a terbium-based triangular magnet. So after the prediction and discovery of topological insulators, a lot of interest grew in the for new quantum states which arise from the combination of large correlations and large spin-orbit coupling. And in particular, I will focus here on new magnetic states which arise in these spin-orbit coupled mod insulators. So as an example, I consider iridium oxides where we have iridium in a 4 plus valence state, meaning that we have 5 electrons in the 5D shell, and in the octahedral crystal field we would have, ignoring spin-orbit coupling for a moment, we would have a T2G states which are filled by 5 electrons. So given the large spatial extension of the 5D shell, we would have expected a metallic state with 1 hole in the T2G band. And it came as a big surprise that, for instance, the layered strontium-2 iridium-04 is actually an insulator, while the isoelectronic ruthenium material is a well-known metal and superconductor. So the reason for that is a large spin-orbit coupling, which splits this T2G in a J-effective 3/2 quartet and a J-effective 1/2 doublet. And now the moderate Coulomb repulsion is able to induce a mod insulating state for this half-filled J-effective 1/2 band. And that's the scenario of the spin-orbit mod insulator, which has been proven, for instance, for this layered strontium iridate materials. Now, the wave function of this J-effective 1/2 is written here, and it has a covariant superposition of different orbital and spin states, and it has a complex component. And that now makes magnetic properties when those electrons hop between neighboring sites via oxygen 2p states, that now can give rise to very new kind of magnetic exchange. In particular, it was pointed out by Yekli and Khalilowin that for the edge-shared iridium-06 octahedra, we have a destructive interference of the in-plane exchange if we have 2 iridiums in the xy plane being connected by oxygens in the xy plane, and only the exchange between the Z components of these pseudo-spins remains. And so that gives rise to such a kind of quantum compass where the spatial direction couples different spin, exchange along different spatial directions couples different spin components. And they also pointed out that we can use such units to build up a honeycomb lattice like realized in sodium iridate, and then we would have along the 3 different bonds a coupling here of the X components, here of the Y components, and here of the Z components. So that's the ingredient for the honeycomb key-type model. And in their first scenario, they considered a ferromagnetic key-type term and additional anti-ferromagnetic Heisenberg exchange, which could, for instance, come from the direct overlap of the extended 5D shells. And they found that the key-type spin liquid is stable unless a certain perturbation threshold of additional Heisenberg exchange comes into play. Later, it was recognized that we also have to consider off-diagonal so-called gamma exchange, which mixes here, for instance, in these for these 2 sides, also an exchange between X and Y component on 2 different sides. And now, can you still hear me, or should I use the microphone? Is it okay? Okay, now it's silent outside. So actually, if we also consider this off-diagonal exchange, we can get various different ground states, even incommensurate, non-coplanar ordered phases. And at the 2 poles of that diagram, we would have the key-type quantum spin liquid phases. Now, let me talk on these materials. So sodium iridate is a layered material where we have this honeycomb, iridium honeycomb planes, and in each plane we also have a sodium atom, and those planes are stacked along the z-axis by intervening hexagonal sodium planes. The same structure is also realized in lithium iridate, where we just replace sodium by lithium, But the lithium iridate has the speciality that we could also have rotations of these honeycomb planes along the third directions, and we can get to three-dimensional versions mentioned in the previous talk, which also fulfill the condition of having threefold coordination of the local magnetic sites and the edge-shared iridium-06 octahedra. The synthesis of sodium iridate was quite straightforward from a self-flux method. We get a nice plate-like single crystals, although they have the problem that they're highly air sensitive, so all the experiments have to be prepared under protected atmosphere conditions. And also we acknowledge that in the tunneling spectroscopy showed us that if we cleave these surfaces, this material we get highly reconstructed surfaces which are lacking 2/3 of the sodium atoms and which have strong atomic displacements. So this means that any surface sensitive properties should be taken with care because the surface is highly reconstructed in this material. Lithium iridate for a long time was only available as powder, and Anton Jesche and Friedrich Freund in my group invented actually a new method to get first crystals of that, and the method sounds very weird because instead of properly mixing the educts for the oxidation process, which is done typically when you prepare oxide samples, here they work with entirely different concept, namely, and that was found by accident of course, namely we place iridium metal and lithium metal in a crucible, but we put them very far apart from each other, and then we heat up just in an uncontrolled way, just in an open box furnace. So we just give hot air, and actually the air shouldn't be too dry because we also need the water content in the air. And then we get the formation of oxides and hydroxides, actually the water acts as transport agent for the lithium hydroxide, and the oxygen in the air acts as transport agents for the iridium oxides. And then on the spikes, which we put then later in the crucible, we get a nice growth of plate-like single crystals as shown here. And these crystals then made possible to determine the magnetic structure of this material. So for sodium iridate, we have a commensurate ordering, a zigzag magnetic order, where we have antiferromagnetic coupling along the key-type Z bond, which equals with the crystallographic B direction. In that case, so such kind of order you would also get just with a ordinary Heisenberg J1, J2, J3 model on a honeycomb lattice, but there is evidence that the key-type interaction is important in this material. And that arises when looking at the diffuse magnetic scattering slightly above Tn with magnetic resonant X-ray scattering. And here it was found that there is all the three different possible zigzag domains are formed as short-lived and short-range clusters above Tn, but they are seen only in the different spin components. So polarization-dependent X-ray diffraction scattering revealed that there is a clear coupling between the direction of the ordering wave vector and the spins and the spin component of the moment. So there is really this entanglement between spin and real space, which is characteristic for the key-type model, and that proves that the key-type exchange is very important in this material. In the lithium iridate, on the other hand, we have a very different kind of ordering. We have a non-coplanar incommensurate counter-rotating order, very complicated arrangement of the moments as indicated here. But there as well, the key-type interaction is very important. What could be seen by looking on these different bonds. For instance, the black bonds here are the X bonds. And for two spins on X bonds, we always have a parallel spin component along the X direction, as seen here. And same holds also for the Y and for the Z bonds, and that is the indication for this ferromagnetic key-type exchange between nearest neighbors, which is important here in this material. Now, to really model the ordered ground states and the excitations requires to involve, in addition to the key-type interaction, several other terms. So not only the isotropic Heisenberg exchange is important, but also this off-diagonal exchange, which I mentioned, which mixes, for instance, along the Z bonds, also the X and Y components of neighboring spins. And then it was found that not only nearest neighbor interactions are important, but also, in principle, all these three terms could appear also for second and third neighbors. So there is a large variety of parameters one could play with. But it was found that in the real materials, in most cases, only a few of them are important. For instance, in sodium iridate, the ab initio study by Rose Valenti's group found that the next neighbor Kitaev ferromagnetic interaction is really the dominating one with 17 millielectron volt. And then there is an addition of a Heisenberg J3 interaction, so which couples the spins along the opposite side of each honeycomb. And as you see here in this zigzag pattern, there is always an antiferromagnetic arrangement between third neighbors, and that's driven by this J3 interaction. For the alpha ruthenium trichloride, it's similar, but there is additionally also the very strong off-diagonal exchange between nearest neighbors, and I come to the effect of that interaction in a minute. Now, for the alpha lithium iridate, in addition to those terms, there's also a strong second neighbor terms, also second neighbor Kitaev term, which causes then this complicated, complex ordered structure. And there is also indication for bond anisotropy, meaning that the Kitaev terms are different along the three different bonds. For the three-dimensional versions, the beta and the gamma lithium iridate situation is even more complex, and there is even next neighbor Choleshinski-Moria interactions included. So from these considerations, it's very highly unlikely that we can tune these materials into the Kitaev quantum spin liquid ground state by just applying pressure or doing some chemical composition. But there is this current discussion whether we can achieve in finding signatures of Kitaev dynamics at elevated energies or respectively at elevated temperatures. And in particular, there is a lot of discussion on the inelastic neutron scattering result. This nice work by the Oak Ridge group work for alpha ruthenium trichloride. They found that over a large energy range, in that case 2 to 15 millielectron volt, in reciprocal space there are sport excitations which have this characteristic shape of this six-fold star. And this has been taken as a signature of the emergent Kitaev Majoranas. But now again, the ab initio work by Rose Valenti's group showed that this omega and Q dependence of this excitation is actually incompatible with what would have been expected for the pure Kitaev model. And it's also inconsistent with what would have been expected for the Kitaev-Heisenberg model discussed originally for alpha ruthenium trichloride, since that would just give Mach-norms consistent with linear spin wave theory. Instead, all these signatures observed in the experiment are well reproduced with the ab initio parameters for K1, J1, and the off-diagonal exchange gamma1 plus J3, which I just mentioned on the previous slide. And they also showed that when you reduce these disturbing terms like gamma1, J3, and J1 and continuously evolve the parameters towards the Kitaev spin liquid, that then the inelastic neutron scattering pattern drastically changes. So all that led them to conclude that what is found is actually not related to the proximity of the Kitaev quantum spin liquid. Rather, it seems that this broad continuum of incoherent excitations is due to the decay of Mach-norms by the strong anharmonicity. And this decay is mainly driven by this off-diagonal, so this highly anisotropic exchange interactions. So they strongly reduce the lifetime of the Mach-norms, and that causes these inelastic signatures found in the neutron scattering. And that tells us that in general we should be careful when considering spin-orbit coupled moments with highly anisotropic exchange, namely that if we experimentally observe a very broad excitation spectra, they may also result just from the anharmonic decay of the Mach-norms. So now I'd like to introduce two new materials. First, this mixed valent iridate, where we have barium-3, indium, iridium-209. We recently synthesized this material. XRD pattern is shown here. It's nice because there is no indium-iridium site disorder and there is no off-stoichiometry. And this structure has the magnetic properties of that structure emerge from this bi-octahedra, so iridium-209 units. And given the iridium valence of 4 plus 4.5, we see that there is one unpaired electron per such a bi-octahedra. So probably we have some molecular orbital states with where spin-orbit coupling needs to be introduced, and then there is an effective moment arising from this one unpaired electron. In the bulk magnetic susceptibility, here I show you log chi versus log t, we see a some nonlinear dependence, so shoulder near 150 Kelvin, which is probably related to the intradimer physics. But then at low temperatures, we see a Curie-Weiss-like behavior below 100 Kelvin with an antiferromagnetic Weiss temperature of about 10 Kelvin. There is no signature of order down to 0.4 Kelvin, and there is no field-cooled, zero field-cooled difference seen in the magnetization. We then looked for MIRS-R data down to 20 millikelvin, and we see that there is no indication for long-range order down to that temperature, and also no frozen moments. We see that the relaxation rate from the MIRS-R experiment increases and then saturates below temperature of 2 Kelvin. We also did NMR experiments in Augsburg with our colleagues, and first here we show the shift of those indium NMR spectra with temperature, and that shift represents the intrinsic susceptibility of the material, and it's very consistent to the bulk susceptibility. We again get a Curie-Weiss-like behavior with a Weiss temperature of minus 10 Kelvin, and interestingly the shift remains finite upon cooling to very low temperatures, down to well below 1 Kelvin. And also we looked for the spin lattice relaxation rate, which is shown here on a double log temperature scale, and at temperatures below 1 Kelvin we see a power law behavior, which and those signatures typically are associated with a signature of a quantum formation of a quantum spin liquid, which gapless excitations. So of course we now need to ask what is the exchange passes which could be realized in this material, and it's a bit more complicated compared to the layered honeycomb materials, because here we have almost equal distances between two iridium sites in plane, which is here 5.83 angstrom. In plane they form a triangular lattice, and out of plane, where the distance is even slightly shorter, it's 5.71 angstrom. And this out of plane connection is, as indicated here, always involves three sides of the lower part of the iridium of the bioctahedra on the upper plane, and three respective of the upper bioctahedra of the lower plane. So we have here an effective buckled honeycomb lattice. So now of course we need single crystals to really determine the anisotropy and to get information whether this buckled honeycomb interactions is more important or the in-plane triangular exchange. But what we could say from the structure is that in any case, for both, we have always a double parallel iridium oxygen configuration, and perhaps that would also allow the key-type exchange in that material. In the last few minutes, I'll now discuss another triangular material, but here now the magnetic moment is not from iridium, but it's rather from a rare earth. So here we have ytterbium 3+, and that means that we have just one hole in the 4f shell. We have 13 electrons, one hole, and that has J equals 7/2 total angular momentum, and there's crystal field splitting, and at low temperature we have a Kramers doublet with an effective spin 1/2. And this material is nice because there is a non-distorted triangular lattice. The ytterbium has inversion symmetry, and it's well separated from the intervening layers, and there is no side mixing between magnetic and non-magnetic sites. The MIRS-R experiments again show evidence for the absence of magnetic order and absence of spin freezing down to very low temperatures. And heat capacity, for instance, shows a power law behavior down to 50 millikelvin. In the inelastic neutron scattering, the Oak Ridge group has observed recently a very broad excitation continuum, but remarkably that was measured at quite high energy, although in absolute scale it's very low energy. The problem with that material is that the dominating exchange is very, very small. It's only 0.13 millielectron volt, which corresponds to 1.5 Kelvin. So in the experiment, which here was done at 0.6 millielectron volt, it's already at several times J, where we study the excitations. And this led us to also look in detail for inelastic neutron scattering experiments. And we found that actually this Born continuum, which is found at low temperatures, here at 0.1 Kelvin, even extends to very high temperatures, 35 Kelvin, which is 20 times the energy scale of J. And it's also seen at very high energy transfer, up to 20 times J. And now, very interestingly, the Q dependence of this inelastic response, which is shown here, perfectly maps with the prediction of the next neighbor RVB state on a triangular lattice. So these are excitations of broken next neighbor RVBs on a triangular lattice. And it's really different to the excitations in the same energy range of the 120-degree ordered state or of a stripy state. And it's also very different from the excitations of RVB if we would have RVBs on further neighbors, on second, third, and so on neighbors. So to our mind, it's the first experimental realization of the excitations of the next neighbor RVB on a triangular lattice. And then we would expect that at low temperatures, we can't break the RVB states if the excitation energy falls below J0. And indeed, it is found that the intensity, if we subtract from the low temperature intensity the high temperature intensity, it's getting negative below the energy scale of J0. And that means that the excitations below J0 have entirely different character. And that haven't been probed yet by inelastic neutron scattering. That's only here first glimpse. And here we really deal with a different type of excitation. And that determines the Pauli behavior of heat capacity, which was found below 1 Kelvin. There is another important ingredient in that material, and that is and that is seen, for instance, if we look in the field polarized state, which we reach at fields above 8 Tesla. So here, instead of having sharp spin waves, we still have a Born continuum. And that modeling this continuum requires, for instance, having a Born distribution of G factors. And indeed, we found that there is a structural randomness in the system, which is very important. And that arises from statistical mixture of magnesium 2+ and gallium 3+. So they push, dependent on the local configuration, they push the oxygens closer or further away from the ytterbium 3+. And that gives this randomness distribution in the crystal field parameters, and it gives a randomness in the G factors. And that may also explain the absence of thermal conductivity in that system. And so it tells us that perhaps the disorder-induced fluctuating clusters here mimic a gapless quantum spin liquid at very low energies. And since the chairman is standing up, I probably need to skip this part on the theoretical modeling of that material and directly go to the summary. So in the first part of the talk, I discussed honeycomb iridates and rustrates. And I showed evidence for the importance of the Kitaev exchange, but in all these cases we have the additional interactions like a third neighbor J and off-diagonal terms which drive us away from the Kitaev spin liquid. Then there is this new mixed valent iridate where we see indications for gapless quantum spin liquid, but here we do not yet know whether we have to treat it in a triangular or a buckled honeycomb lattice or even a combination of both. And then there is this Raworth-based triangular magnets where we have at high energy the realization of next neighbor RVB excitations on a triangular lattice. And there is also continuous low energy excitations observed in heat capacity and μSR. They must have different nature, but one has to be careful because there is structural randomness, and that may also give rise to randomness in the magnetic exchange. Okay, thanks very much for your attention.